Let's try and get our minds around what we mean by vapor pressure by doing the following thought experiment. Let's say we have two buckets filled with two different liquids, and we put our hand over the top surface of the liquid above each bucket. Let's say that with the bucket on the left, we feel a significant pressure from the liquid particles turning into the gaseous phase, and when they do that, some of them bump into our hand, and we sense a pressure. On the right, we also sense a pressure, but not as great of a pressure. We would say that the substance on the left has a higher vapor pressure, and the substance on the right has a lower vapor pressure. Of course, we can't really do this. We can't feel vapor pressure with our hands because they're not sensitive enough. But it's a good mental image to help us understand what we mean by vapor pressure. Now, if the substance, that is, if the liquid on the left has a high vapor pressure, that would mean that the intermolecular forces between those liquid particles are relatively weak. Therefore, those liquid particles easily escape from each other and go into the gaseous phase fairly readily. On the right, things with low vapor pressures tend to have stronger intermolecular forces because those particles in the liquid phase tend to hang on to each other more tightly, so fewer of them turn into the gaseous phase. So let's define vapor pressure. Vapor pressure is a measure of the tendency for liquid particles to enter the gas phase. That is, it is the pressure exerted by a vapor in dynamic equilibrium with its liquid or solid phase. Examples of substances with high vapor pressures, that is, volatile substances. Volatile substances are those with high vapor pressures. I like to think of things that you can smell right away when the cap is off as being substances that have high vapor pressures. Rubbing alcohol, mineral spirits, nail polish remover, often stains and urethanes that are used in woodworking. I think of those things as having high vapor pressures. They very easily, very readily escape from the liquid phase into the gaseous phase. This statement at the bottom is actually two statements in one. As temperature increases, vapor pressure does what? And as temperature decreases, vapor pressure does what? Let's think of a bucket. Let's make it a metal bucket filled with water, and we put our hand over the top and we feel a certain pressure. Now we put that metal bucket on a stove and we start heating it, and we hold our hand over the top. What happens to the vapor pressure? As temperature goes up, it's going to increase, and as temperatures go down, vapor pressures decrease. Because of its strong intermolecular forces, water has a relatively low vapor pressure. Now, what's the most important intermolecular force in water? And that, of course, is hydrogen bonding. We have a graph here of three substances, chloroform, ethanol, and water, and you can see for each of those, as the temperature increases, the vapor pressure increases. That was the statement at the bottom of the last slide. And you can also see that of these three, water has the lowest vapor pressure. For example, here at 60 degrees Celsius, water has a vapor pressure of about 20 kilopascals, ethanol has a vapor pressure of about 50, and chloroform has a vapor pressure of about 100. And that's because the intermolecular forces in water, primarily hydrogen bonding, those are fairly strong forces. So those water particles in the liquid phase tend to hold on to each other relatively strongly, and so that not many of them tend to go into the gaseous phase at a particular temperature compared to other substances. Boiling occurs when the vapor pressure equals the confining pressure. Now typically the confining pressure on, say, a bucket of liquid is from the atmosphere. Let's take three examples here. Let's say that on the left, due to the atmosphere, the confining pressure isn't very large. What that means is to make this substance boil, that is, to make its vapor pressure equal to that low confining pressure, we don't have to heat it very hot. In the middle bucket, the confining pressure is larger. we would have to heat this liquid to a higher temperature than that same liquid on the left in order to get the liquid in the middle to boil. And if the confining pressure were even larger, we would have to heat that same liquid up even hotter in order for it to boil. The normal boiling point is the boiling temperature of a liquid at 1 atmosphere of confining pressure. In other words, at the normal boiling point, the confining pressure and the vapor pressure both are 1 atmosphere. If the middle diagram represents both confining pressure and vapor pressure equaling 1 atmosphere, the diagram on the left shows some situation where both the confining pressure and the vapor pressure are less than 1 atmosphere. This is the situation we would have at high altitude regions, like Denver. On the right, we see that the confining pressure is larger than the normal confining pressure. That would be the type of situation we would have at very low altitude regions, the Dead Sea, for example, or what you have whenever you have a pressure cooker. With a pressure cooker, that confining pressure is increased well beyond the normal confining pressure, and for that reason, this water that you're heating and the food that you're cooking have to be heated to a hotter temperature than 100 degrees, and it cooks a lot faster.